Okay, so here's where we were last time. We were talking about how to compute centroids. And we're looking at this example where we have the upper semi-disk of radius A. So that's this shape here. And density being 1. By the way, again, reminder, if the density is not given, if they just say, what's the centroid of this geometric figure? Assume the density is 1. That's what that means. Okay. All right, so I made a quick observation that x bar is 0. And I wrote here bisymmetry. I want to emphasize, again, this is the last thing I said last time, I don't want to take a physical symmetry argument, right, and say, I understand what would happen if I had a sheet of metal shaped like this. I just understand physically how that would balance, the forces. Come on, it's the same forces on both sides. That physics arguments are not what we're interested in. There's not a physics class, okay? So here I want to see a math argument. So there are details that you can put down that refer specifically to this integral. That integral is equal to 0 by symmetry. We had a conversation last time about how to make a symmetry argument. You have to identify what is the line, what is the formula for reflection over that line, and how does that formula for reflection algebraically demonstrate that the function has odd symmetry. So that's what I want to see here. I do think this is a nice exercise. I hope you'll take the time to actually do it. Persuade yourself. Fill in all those details. How would you write that down on an exam? Right? Nice exercise. That said, it's integrals equal to 0 by symmetry, which is just cut our workload in half. Isn't that nice? This is one of the 20% of integrals in my undergraduate career that I was able to make a symmetry argument about. Okay, so on the other hand, what's the y-coordinate of the centroid? So where on the y-axis? Is it here? Is it there? How do you know where the y-coordinate is? There's your formula for y bar. Right, straight out of that. What's most interesting about this is how to evaluate the double integral, of course. Now, double integral is an iterated integral. So that's something, you write that down. You go through the usual slicing process. Here you'll notice I'm doing my y slicing first. Right, so y starts at that point, let's say. That's where y is clearly 0. Ends at that point where y is, of course, clearly a. Y bounds are 0 to a, etc., etc. Finding the x bounds, I'll go ahead and say, for a given value of y, the x bounds correspond to these 2 points. The points are on this curve. That curve has an equation that you'll, of course, recognize. Solve for the variable you're interested in. Okay. And then crank, and it works out. This is single variable calculus. Y'all should make sure you are strongly comfortable, perfectly proficient with the Calc 2 methods that go into computing that double iterated integral. We will assume that you are proficient with that, and if you can't, then it will be a problem. Okay, so I know Calc 2 might have been a while. It was months and months ago. For some of y'all, it might have been a year ago, right? And there's a tendency to think, oh my gosh, I thought I was done with that class. I thought I'd never have to do a trig substitution ever again. So not so. And by the way, classes that list multivariable calculus as a prerequisite usually require students to be able to do stuff like this. Not that this is a trig substitution, but to be able to crank out non-trivial integrals. Okay, so make sure you can do that. Single variable calculus never goes away. Okay. All right, so here's another thing I'll point to. I made this slicing choice. Y slicing on the outside. Right? I could have done it the other way. Could have done the X slicing on the outside. Here's what that looks like. And at a glance, it is not particularly clear or obvious which way you should slice. Neither slicing order has you slicing through corners. Neither variable is sort of obviously the independent variable or obviously the dependent variable. So there's kind of a, do it whichever way you like kind of aspect to it. Nevertheless, one of these is easier than the other. You can probably just see from the amount of pencil on the page here that this one was a little longer, and this one was a little easier. So I want to very quickly talk you through what I think would be a kind of a, how to kind of handicap this in advance. I mean, what do you sort of think? I mean, how would you strategize? I'd like to know how to always pick the one that's going to be easier, right? Wouldn't you? I certainly do. So let's look at this integral, and I ask, what am I most afraid of? And that's the square roots, right? I mean, oh my gosh. I mean, this is in the bounds of the inside integral. That means that's going to be part of the integrand of the outside integral. And when there's square roots in an integrand, this has got all sorts of potential to be bad. Lucky break, wasn't that bad here. Nevertheless, this was the worst one. Okay. So, why did the square roots here turn relatively bad, and why did the square roots here turn out to be not so bad? And roughly speaking, I'll argue as follows. These square roots I plugged into a square, and square makes square root go away. Right? Well, that's nice. Okay. Whereas here, these square roots plugged into not a square, and I didn't write the antiderivative, but the antiderivative here, of course, is xy, and you're plugging in the square root for just x, which is not squared, right? So you can, again, you can sort of see this coming a little bit. You can look and see, I see square roots, I don't like square roots. This is not going to produce anything squared, whereas this is going to produce a square. And you can, again, without actually writing out the antiderivative, without explicitly plugging anything in, you can just see that there's something advantageous about doing the y antiderivative first, therefore on the inside, to make a square that'll kill that square root, and then it's all downhill from there. Okay. So anyway, that's a point of view that I encourage you to kind of always be on the lookout for. When you're not obviously slicing through a corner, which strongly suggests one order of slicing, or when you don't obviously have an independent variable, a clear choice of independent variable that suggests slicing the other way. Try to sort of anticipate how the algebra is going to work just a little bit, and you might save yourself a little trouble. Okay. All right, moving along. I want to talk about this thing called Pappus' theorem, very often referred to as the Theorem of Pappus. And my theory on that is that they call it the Theorem of Pappus because no one's really 100% sure whether it's apostrophe or apostrophe S if you make Pappus possessive. Right? So we avoid the problem completely by saying Theorem of Pappus. Yeah. I looked it up, by the way, one time, and apparently there's not a uniform consensus on what the right answer is on that. Right? And so it's not so much avoiding the possibility of making a mistake as avoiding an argument with people of different, schools of thought on the question. Okay, so here's the question we're going to consider. Suppose that we have a line. Suppose that we furthermore have a plane containing that line. And furthermore, suppose we have a two-dimensional region sitting inside of that plane entirely on one side of the line. So this is our scenario. The question is, given this scenario, if I were to take this area and if I were to rotate that area around that line, thus generating a solid, I'm not going to try to shade in, but you can see there's a solid there, that kind of a donut-like thing that gets made, right? How would you compute that volume, and what does that have to do with the area? Now, quick reminder, we do know one relation between volume and area, not in this context, but if you have an area like this, and if you drag that area in a straight line, right, it makes a sort of a generalized notion of a cylinder. The area times the distance that you drag it gives you the volume. I mean, that's a basic geometry formula. So we're hoping for something kind of like that. But it's hard to say, right? Because look, this little piece of area right here sort of gets dragged that far, whereas this little piece of area over there gets dragged a greater distance. So which distance are we thinking we might multiply by? I mean, it's really not clear. Right? All right. So here's the strategy. And by the way, I know you all have done volumes of rotation in high school calculus classes. This is different because, well, for one thing, here my line is angled. Could be any line, right? And also, I'm going to approach this with a double integral to great benefit, as we'll see in a moment. Okay. So the idea is, don't think in terms of slicing like this. That's a single variable calculus mindset, right? Also, don't think in terms of the cylindrical shells structure that you might recall from high school as well. Again, that is also ultimately a single variable mindset. Ultimately, what that says is, I'd like to think of this area, and I would like to think of taking single variable calculus type slices, right, of that area. And that's a very, Calc 2 point of view. Not there's anything wrong with that, right? But let's take a more sophisticated point of view. Think about each little individual piece of area from a double integral Riemann sum point of view. And I argue, you have to appeal to your geometric intuition. If I were to take each one of those individual pieces of area, and if I were to individually rotate them around to make the little, onion rings, if you look at all of the individual onion rings that you generate by taking all of those, I don't have any knives that will slice this way, right? But if you were to take each little piece of area, rotate each one separately, independently, to create an onion ring, if you add up the volumes of all those onion rings, that'll give you the total volume of the donut. Yeah? Plausible? Okay. So here's how we write that down. So this is a nice application of a double integral. This little piece of area, dA, and you multiply it by the distance. I can totally compute that distance. It's 2 pi r, where r is, this, that right there is r. Whatever the distance is from that point to the axis you're rotating around, right? It's going to vary. It's not constant. It depends on which piece of area you're talking about. But there we've got, roughly speaking, a high school geometry situation. Obviously, it's round. I'm dragging this thing around a round path instead of a straight line path, but all of the points are being dragged the same distance. Or, if you prefer, I could imagine taking a pair of scissors, snipping this, onion ring, right? And then just straighten it out. And now it's a little piece of area that's been dragged a straight distance, right? So, because it's a microscopic little teensy-weensy little slice, because we're taking a limit as those get smaller and smaller, we can make this argument directly. And then add those up. You take all of these individual volumes. Take all of these individual little pieces of volume. Add them up over the entire region. Keep in mind we've got this whole thing over here, right? So let's add up over that whole domain, and there's a double integral that will compute that volume for you. Now, I'm not suggesting that you compute with this. It turns out there's a wonderful little beautiful moment that's about to happen here. Hard to see this coming. Nevertheless, I think it's worth recognizing, hey, look, check it out, Riemann Sum. Okay. That said, here's the beautiful point. If I were to take this formula, obviously I can factor out the 2 pi. If I were to then furthermore multiply and divide by a, then what we get here is something that we recognize, kind of. That looks like the formula for a centroid, doesn't it? 1 over area, double integral of distance times dA. And it's morally equivalent to, if density was 1, that's exactly what this is. Now, okay, not quite. Look, that one is about y coordinates. There's a y axis. I'm measuring, distances. That distance there is distance along the y axis. What axis are we talking about here? Well, okay, sure, there isn't really an axis there exactly. There's no r axis, but look, I could make one. Right? I could just make an r-axis there. And for each little piece of this region, keep in mind we've got a region there. Right? For each little piece, I can talk about, wherever it is, I can talk about its distance along that axis, which, by the way, of course, is just a distance. It's just r, what we've already called r. So that thing that's in the integrand, it really is a coordinate. It's just a coordinate along an axis that we hadn't, noticed yet. So in the same way that this formula gives us the distance for this y bar formula here, that gives us the distance from the centroid to the axis perpendicular to the y-axis. Likewise, this formula here gives us the distance from the centroid, wherever that centroid is, to the axis perpendicular to the r-axis. Namely the line that I'm rotating around. So that is it's a distance. It's an easily computed distance. Simply a distance from a centroid to a line. So, punchline then, here's our formula for computing that volume. The volume is, it's A times 2 pi r bar, and if you shuffle things around a little bit, you get A times 2 pi r bar. Namely, writing that a little bit differently, area times the distance traveled by the centroid. So that gets us back to, our original idea was, look, area, as we move this thing around, as we drag areas, you feel like as you drag areas, you make volumes, and volume should be area times, in some sense, the distance, but different points travel different distances. Where's my thing? Yeah, different points travel different distances. Which point do we look at? Answer, centroid. Just look at the distance traveled by the centroid. So here's a lovely little example of how this plays out. Suppose I want to compute the volume of this, volcano-looking thing there. That being what you get when you rotate this triangle around this line, where r is equal to 1, where x is equal to 1, pardon me. Well, look, at Calc 1 point of view on this, you're making slices one way or the other. You could have cylindrical shells. It's going to break up into two separate integrals. Or you could make washers, in which case you'll only have one integral, but nevertheless you're doing an integral. The easy way to answer this problem is to say that's a Pappus's theorem problem. And I know where the centroid is. It is perfectly obvious where the centroid of this triangle is. It's right there. And here's the axis that I'm rotating around, and therefore the distance traveled by the centroid is 2 pi r bar. R bar is clearly 1. And so the volume that I'm interested in, this total volume, is that area times distance traveled by the centroid. So boom, no integrals. Right? This is a neat trick that what we have here is a one question that has been turned into a different question. This happens sometimes in math. Methods are not always, here's a question and let's create a tool that computes it directly. Sometimes what we end up with, as in this case, is a method that allows you to turn one question into a different question. And even though those two questions are related to ultimately the same integral, sometimes one of the questions is obvious. Where's the centroid? Perfectly obvious. Versus, what's the volume? Oh my God, well that's a much harder question. Here's the observation in reverse. What if I take this semi-disk and rotate around the x-axis? Well, now I already know the volume. When you take a semi-disk and rotate it around, you get a sphere, 4/3 pi radius cubed, right? So the volume here, in this case, the volume is something that I know. But the location of the centroid, not so clear. A couple pages back, we had to kind of crank out a non-trivial double integral to be able to compute where that centroid is. Here, though, because we can relate these two questions to each other, and because the answer to the volume question is ancient history, long since known formula, 4/3 pi radius cubed, Pappus's formula allows us to compute our bar. And there you go. Notice we get the same answer. Pappus theorem is a pretty neat tool. Pretty nice. I've already spent more time than I should have on Pappus's theorem, but I think it's a really, really interesting discussion. Let me blow at light speed through this next discussion about the second version of this, and that is, instead of rotating an area to make a volume, what if you have a curve that you rotate around to make an area? Kind of a lampshade looking thing here. Right? So what's the relationship between where the curve, what the length of the curve is, let's say, and what the area of the lampshade is? Morally, kind of analogous question. You could make a very analogous argument that involves a kind of integral that we haven't quite talked about yet. So again, I think this is a good candidate for us to not talk about. You're not responsible for this derivation here, but the argument remains. The conclusion, remains that the area is the length times a certain distance. In this case, it's the distance traveled by the centroid. For example, suppose you want to know the location of the centroid of that curve. I emphasize, that's like a wire. I am not asking here, we are not interested in the location of the centroid of that area. Not at all. We're talking about the curve. That's a different thing. It's a very different arrangement of mass, right? And you can't just say, oh, this vaguely reminds me of this other shape because I arbitrarily feel like the x-axis automatically matters. Right? That is a complete nonsensical argument. You can't do that. So where the centroid is it's really not clear. But I know what happens when I take that area, and when I rotate it around, I get a sphere whose area formula I already know. Right? And then by connecting through Pappus's theorem, I can compute the location of the centroid, and there it is, as it turns out. Okay, nice application. Okay, so here's another physics thing. I commented a while ago that this is not a physics course. When we have more time than we really need, which happens to me sometimes, believe it or not, I do enjoy talking through the physics argument for justifying what is this thing called moment of inertia. It is ultimately a very natural physics thing. You're welcome to read this if you'd like. It's pretty readable, I think, if you're in fact interested. Likewise, you can come to office hours if you want to hear me give a short discussion of why we would care about this thing. But I'm just going to have to go down to the punchline here. This thing that we are interested in here is called moment of inertia. This is a formula for it. It's a double integral r squared dm. R, what is R, you ask? If you have a mass here, we're going to be doing a double integral over that mass, no surprise. On each little piece, we need to talk about how far is that piece away from the axis that we're rotating around. That distance from where you are to what you're rotating around, that's what we're calling R in this formula. And so that's this thing here. R. There we go. Okay. Very, very quickly, the reason we care about moment of inertia is because it is useful in a important formula in physics. If you have a mass that's rotating around, and you ask the question, well, how much energy is there in the rotation of that mass around an axis? You already know about kinetic energy, what I'll call linear kinetic energy. If something's moving in a straight line with a velocity v, 1/2 mv squared. You all memorized that in probably 9th grade physical science class, or whatever that is called these days. But if it's going around in a circle, different pieces are moving at different velocities. Something that's rotating around, something that's on the back side is traveling a greater distance every rotation. Therefore, it is going faster. Something that's on the near side is hardly moving at all as it goes around. So what velocity do you pick? Anyway, nice punchline is this formula, and the object in here, this thing, is called the moment of inertia. Okay, office hours if you have more questions about that. So do keep in mind, as I just mentioned, this thing called R. You cannot just memorize a formula for it. A lot of people like to say, R, I remember that letter. That letter always means square root of x squared plus y squared. And I'm sorry, it doesn't. If you're talking about polar coordinates, then that is how you use one of the coordinates in polar coordinates is connected to that formula. But it's not the only use of that letter. R, tragically, is one of the most overused letters in the alphabet. When you're doing math, R means different things in different contexts. And in this situation, R does not always mean square root of x squared plus y squared. As previously discussed, what R always does mean is the distance from whatever point you're looking at. Keep in mind, maybe you're doing a double integral over a region like that, so you're breaking it into little pieces, and on each little piece, namely for any given location, what R is the distance to the axis you're rotating around. The axis you're rotating around, let's say maybe here you're rotating around the z-axis. Do you imagine this yellow shape rotating around that red z-axis? R is that distance. And if this point is x comma y comma, I'm going to say z, but obviously it's in the xy plane, so it's 0. That distance easily computed, in this case, is square root of x squared plus y squared. But if you're rotating around a different axis, let's say, there's plenty of situations where maybe this region is rotating around that axis. Well, this is a very different situation, and now the distance from there to the axis you're rotating around, that is clearly not square root of x squared plus y squared. Right? It's the absolute value of y. In this case, it happens to be y is always positive, so it's also just y. But I'll put the absolute value in there as a reminder that it is got to be positive. Different situations, you have different formulas. Right here, if you're rotating around the y-axis, then the distance is not y. Now the distance is x. Absolute value of x. If you're rotating around some other line, you could imagine a scenario where, I don't know, you're for whatever reason rotating around something like that. Then now the distance, it's the distance from there to there, and that's not hard to see. Absolute value of x minus a, where a tells you what line it is. So please do not just memorize. There's only so many different cases. This thing can only be rotating around so many axes or so many different kinds of lines, and in each one of those cases I'm going to memorize, in that case the formula for R is, there's too many cases, right? What if the region is not in the XY plane? What if the region is over here in the YZ plane? Okay, well now there's a whole nother long list of cases. What if it's in the XZ plane? Well, now there's another whole long list of cases. This is not a This is not a plausible long-term solution. What you have to do is draw a picture every time, look at the picture, and infer, what is my generic formula from a point on that region into the axis that I'm rotating around in this case? You just got to look at it every time. Quick example. Suppose you have this region here. And you want to compute the moment of inertia as that rotates around the x-axis. Well, there's your picture. Here's the distance from a generic point to the axis that you're rotating around. You look at the geometry of this picture. Clearly R is equal to y. right? And therefore your formula for moment of inertia, we're trying to find moment of inertia. There's your generic formula for moment of inertia, and it simplifies to this in that case. And now you've got a double integral, off to the races. Let you guys crank out the details here. Again, reminder, it's assumed that you can do these kinds of integrals. Notice you end up with a weird one here. Integral of sine cubed. Weird stuff comes up. Right? And so all of those single variable calculus techniques that you learned long ago, yeah, they come up, right? The world's full of them, so you've got to remember the trick on this one. So make sure you remember the trick. Here's how it goes in this case. If you feel like you might need to brush up on Calc 2, now's the time. Okay, so moving along, new topic, we're going to talk about triple integrals. And I'm going to try to set a perspective on this first. Ultimately, the big idea that you should keep in mind about triple integrals is kind of analogous to the big idea that I wanted you to keep in mind about double integrals, which was the same idea that I wanted you all to keep in mind about single variable integrals, namely these are Riemann sums. Very importantly, Riemann sums are the thing. There's a tremendous amount of applications out there, endless applications, where we'll see some examples coming up soon, right? But where, as it turns out, you need to be able to take this thing, chop it up into little pieces, and create this algebraic structure called a Riemann sum, to answer your question. There's just so many applications where this is the case. So, reminder, it's very important to not think of single variable integrals in the way that gets pushed really hard in single variable calculus classes. Namely, the point of view that I feel like is routinely pushed is that, yeah, we got to write down formalities, Riemann sums, blah, blah, blah. That's just mathematicians being nerds. But that integrals are area under the curve, and students just come away feeling that's what an integral really is. This is a huge mistake. Single variable integrals are Riemann sums. That's what they have to be able to make applications. You'd be surprised how few times in my undergraduate career, keep in mind, mathematician, ivory tower weirdo, sure, I understand. Physics major too, right? I did a lot of really practical, real-world physical stuff as part of my physics major, and almost never did I have to compute an area under a curve. It almost never happened. I think it happened once or twice. It's a relatively rare application. Right? What you need single variable integrals for is because the world is chock full of other kinds, not area, but other kinds of applications that break down as Riemann sums. So application to Riemann sum. Riemann sum you write as an integral. Compute with the fundamental theorem of calculus. Area doesn't have anything to do with it. Okay, so that's just a reminder. Same point with double integrals. Double integrals are Riemann sums. That's the big deal, right? And that will ultimately be the same point about triple integrals. Triple integrals are Riemann sums. And it's really important to think of them that way. Okay. All right. Now that said, it remains that we got to have a way in our minds to think about, to kind of visualize these things. And I know everyone likes to continue to think about single variable integrals. And Riemann sums are very important. Fine, Bray makes a point, but I think of them in my mind as areas. And I'm going to try to dissuade you from that. And this is the moment where I think I have a really good case to make. Here's how that case works. Here's a picture of two different ways to think about a single variable integral. There's our single variable integral. Keep in mind the Riemann sums. That's the big point. Option 1, you can think of it as area under a graph. Okay, sure. Option 2, you can think of a different physics application. Let's say the mass of a one-dimensional rod. Well, the one on the left has a strong appeal. Right? I can see more. It's more spread out. It's more geometric. It's hard to look at a one-dimensional rod and see density. So there's a strong appeal. I get that, right? The blue picture over there, very tempting. All right. Here's double integrals, kind of the analogous picture for double integrals. Here's a double integral. And on the one hand, fully recognizing the Riemann sum is the thing, blah, blah, blah. But yeah, but when you visualize it, you can think of it as volume under a graph surface. Okay, sure, yes, you can. But you can also think of it as representing the mass of a two-dimensional region. And again, pro-con, but yeah, look, there's a strong appeal for going to the geometry. You can see it. It's more spread out. I can visualize. It's hard to visualize density geometrically. Okay. It kind of seems like we have 2 wins for the geometry at this point. So look, here's where I win the game. Notice the pattern, right? Single variable integral. Area under the graph of a single variable function, which is, single variable integral, single variable function, picture is 2-dimensional. Double integral, function of 2 variables. It's a 3-dimensional picture. Where do we go from here, right? If a triple integral is going to be kind of the analogous algebraic thing, what's the next step here? Well, I'll tell you what that next step. If we say I would like to visualize this as representing how much it's not area, volume, and then what comes after volume, right? Geometrically, area is 2-dimensional, length is 1-dimensional, area is 2-dimensional, volume is 3-dimensional, and after that is something that we simply cannot visualize, right? So crash and burn, fireball of failure. There is no way to visualize Riemann sums, triple Riemann sums, from that sort of, how much space is there, you might say, under the graph. That's a loser. Okay. So whereas, let's think about the mass examples. 1-dimensional Riemann sum, I can think of that as mass of a 1-dimensional rod with a density function of 1 variable, and it's a 1-dimensional picture. 1, 1, 1, 1, 1. Double integral, 2, 2, 2, 2, 2. Whole picture's 2-dimensional. And no problem. You go to a triple integral, well, it stands to reason. We'll talk through the rationale here, but maybe it represents the mass inside of a 3-dimensional region with density, mass per unit volume. Perfectly relatable. Right? So, all right. So, and I think this is very persuasive. Certainly this is very persuasive for me when I was y'all's age. The problem with this point of view here is that it just puts you on a road that's doomed to failure. There's really nothing wrong with that point of view in a single variable calculus context, because in single variable calculus you're not going below this line, and so who cares what it leads to? You're not going down that road anyway, so who cares if the road has a roadblock? Right? But here we are in a multivariable calculus setting, and I strongly encourage you, please don't try to go through this course thinking of that's your picture for single variable integrals, that's your picture for double integrals, and that's your picture for triple integrals. You've got 2 3-dimensional pictures that represent 2 algebraically very, very, very different things, double integrals and triple integrals. And that's so confusing. You're gonna tie yourself into little mental knots, and you're gonna never straighten them out. Okay. So, I urge you, please try to think of these Riemann sums, aka integrals, right? Integrals, of course, most fundamentally, definitely Riemann sums. Got to be your lead point of view. But think of them at least also from these points of view here. Mass of a 1-dimensional thing, mass of a 2-dimensional thing, mass of a 3-dimensional thing. Strong analogy. No sort of intrinsic source of confusion here. Okay, all right. So I think that's a really good point. Of course, I'm not suggesting that you should abandon these altogether. I just want to make sure that you give heavy emphasis to these that tend to get underappreciated. as you're going along. They're sort of underappreciated in preference to the crutches over there, the geometric crutches over on the left. I want you all to start taking an active role in encouraging yourself to think about integrals as representing masses instead of area and volume. Okay, all right, enough of that. Okay, so here's the formula stretched out. Breaking up a region into, here, let me go back to the picture over here. If I wanted to compute the mass inside of this thing, right, I would slice in 3 different directions. I would break up this volume into little boxes. They're not sub-intervals. They're not sub-rectangles. They're sub-boxes. Right? On each of those little pieces, I can very comfortably argue the amount of the amount of mass in that little piece is volume times density. Here's the good news. This is an even easier argument than it is in 1 and 2 dimensional cases. In the 1 and 2 dimensional cases, you kind of have to reinterpret reinterpret density. We all grew up thinking of density as mass per unit volume. Right, that's what they always told me in middle school. Mass per unit volume. That's the definition of density. And now we got to think of mass per unit area. New concept, right? Mass per unit length, new concept. Here we get to revert back to our middle school point of view on density. It's mass per unit volume again. Good old density. Right? So that's great news. And then, of course, we add up over the entire region all of the little sub-boxes that I get when I slice and dice this solid. Okay. So here's, again, how you write that as a Riemann sum. There's a bunch of little pieces of volume. Each volume you're going to multiply by some sort of a density is the way I like to think about it. By the way, there's different kinds of densities. We'll come back to that in a minute. And then you add up over the entire region. Now, there are 3 indices because you're slicing this way, you're slicing that way in addition to this way. Right? There's sort of 2 slices, and then you also are slicing that way. Okay. All right. So I've already talked through this bit here. If you take the geometric point of view of area under a curve, volume under a surface, you lose the game at the end. Right? So you gotta let go of that as much as you reasonably can. Think about things from the mass and density application. At least make sure that you can think about integrals very comfortably from the mass and density application. A quick reference. There's going to be other kinds of densities that we're going to see in the following sense. There's mass per unit volume. Right? Hey, if we were talking about concentration of particulates in the atmosphere, that wouldn't be so much mass per unit volume as number of particles per unit volume in the atmosphere, right? Or maybe I'm doing a population density of, maybe there's a bacteria floating around in the air. Then the population density of volume would be, number of bacteria per unit volume. Right? So what the stuff is varies. And we're going to see in Chapter 15 that there are not just physical things like mass and bacteria and pollution particulates that we want to keep track of per unit volume. There are geometric constructions. I'll have to be real vague about this. There are geometric constructions that I want to think of as relating to volume by way of a corresponding notion of a density. There's a lot of groundwork we have to lay before I can actually make any sort of sense out of that. But thinking about triple integrals as relates to stuff accumulating in relation to densities, just like the mass application, just different stuff. That's going to be a big deal in Chapter 15. So yet another vote for the density point of view on integrals. Okay, we already talked through all that stuff. Okay, so how do triple integrals work? I'm just going to assert we're not going to get rigorous here in Math 212, but in the same sort of analogous to the idea that double integrals could be computed with iterated integrals, there's an analogous thing for triple integrals. This is just how the details work out, and I think it's highly plausible. Reminder. For the for the outside integral, remember that terminology, outside, inside. For the outside integral, we put here the range of the values of that variable over the entire solid. That's sort of the easy part. Then you fix a value of that outside variable. For the inside integral, you look at the range of values over just a slice, right? So we fixed a value of the outside variable, and then only on that slice do we look at the resulting range of values of the inside variable. Right? So we did a bazillion examples of this sort of thing. Said a little bit differently, you start on the outside, you look at the range of values, then you fix that variable, move inside to the next inside integral, look at a slice corresponding to that fixed value of the outside variable, and then you look at the range of values of the next variable. Same pattern for triple integrals. Different picture. Obviously, it's a three-dimensional picture now instead of a two-dimensional picture. But your outside variable, let's say x here. Right? You look at the smallest value of x. You look at the largest value of x. No surprise. You identify those first and last x slices by sort of, well, where's the first point that you hit? Where's the last point that you hit as you slice perpendicular to that axis? That gives you your outside bounds. Okay? Just like with double integrals. Now, just like with double integrals, we now fix a value of that variable. We look at a single value of that outside variable. We fix that. Namely, we look at this x slice. Reminder, x slice means a slice perpendicular to the x-axis. Slice corresponding to a fixed value of x. Thus the terminology x slice. Now on that x slice, I look at, my next variable is y. So I look at slices perpendicular to the y-axis. I appeal to your geometric intuition. If I take slices perpendicular to the y-axis of a slice that's already been taken perpendicular to the x-axis, think about, it's we've got something this way, and we're slicing it that way. Those slices actually look like little line segments, like that. And we can talk about where is the first one. I put it over there, y1, and where is the last one? That's your inside bounds. Now note, just like with double integrals, the inside bounds depend on the value of the corresponding outside variable, right? We fixed a value of x over here, thus defining the x slice, and so the y bounds depend on the x outside variable, thus functions of x. Okay, last, now we look at a y slice of our x slice. So on that x slice, we furthermore fix so x is fixed, then we furthermore fix a value of y, and on that y slice of that x slice, well, all we have left is a little french fry. Right? A little twig sticking up there. And on that, we look for, running out of colors here, where's the first value of z? Where's the last value of z? That gives me z bounds. Of course, the z bounds are functions of x. We fixed x long ago. They also depend on y, because we just got through fixing y2. So the inside variables, the z1 and z2 are functions of both of the variables further to the outside. The inside variables are functions of two separate outside variables. So that's what it's going to look like. We'll start seeing examples next time. Y'all have a great weekend. See you later. As you may have noticed, I was running late. I apologize, but I didn't check attendance yet. So let me do that before y'all go. Let's see here. I'll try to be super quick with it. I think I